We have already talked about the bond angles that correspond to each molecular geometry. For example, the ammonia molecule, NH3, has 4 domains, 3 of which are bonds and 1 of which is a lone pair. Since it has 4 domains, we expect its bond angle to be 109.5 degrees. Its experimentally measured bond angle is actually 106.8 degrees, slightly smaller than expected. This is because the lone pair actually takes up extra space. It's a little counterintuitive that not having an atom attached would make it bigger, but the atom actually serves to rein in the electrons a bit, so not having it means the electrons take up more space. I don't expect you to know the exact values like 106.8, but you should know that the angle will be less than expected whenever there are lone pairs on the central atom. For example, for the water molecule, you could report that the bond angle would be less than 109.5. You would generally use the less than symbol and then write 109.5. Double bonds can also make bond angles smaller than expected. They take up more space than single bonds, so they can push atoms closer together. For example, formaldehyde is trigonal planar, so we expect its bond angle to be 120 degrees. In actuality, the bond angle is 118 degrees from hydrogen to hydrogen because of the CO double bond. Triple bonds also take up extra space, but they are always linear, so the bond angle remains 180 degrees. Since trigonal bipyramidal molecules have 2 different positions, it matters where the lone pairs are. They are always going to go in the equatorial positions, not the axial. This is because the equatorial positions have the largest angles between them, 120 degrees. This gives the larger lone pairs extra space. This is why ClF3 and similar molecules are T-shaped, like in part B of the figure, rather than trigonal planar, like in part C of the figure. You have learned to do several things that all build on each other. Given a name, you should be able to produce the formula. For example, you should have memorized that ammonia is NH3. From the formula, you should be able to draw the correct Lewis structure using our 5 steps. From the Lewis structure, you should be able to determine the number of domains. For example, ammonia has 3 single bonds and 1 lone pair for a total of 4 domains around the central nitrogen atom. From the number of domains, you can know the electron domain geometry. For example, if a molecule has 4 domains, it has tetrahedral electron domain geometry. You can also determine the approximate bond angle from the number of domains or from the electron domain geometry. A molecule that has 4 domains and is tetrahedral has approximate bond angles of 109.5 degrees. You can also count the number of lone pairs on the central atom. Ammonia has 1 lone pair on the nitrogen. From the number of domains and number of lone pairs, you can deduce the molecular geometry. The ammonia molecule has 4 domains, and one of those domains is a lone pair, so it must have trigonal pyramidal molecular geometry. Finally, if there are lone pairs or a double bond on the central atom, put a less than sign in front of the bond angle. Since ammonia has a lone pair on the nitrogen, you would report the bond angle as less than 109.5 degrees. Up to this point, we have focused on molecules which have 1 atom at the center and the rest around that central atom. But what about larger molecules? For larger molecules, we focus on 1 central atom at a time and do the same sort of analysis as we've already been doing. For example, in the methanol molecule, we can treat the carbon as a central atom or the oxygen as a central atom. First, we'll start with carbon. Again, we can count the number of domains. It has 4 single bonds, so 4 domains. 4 domains corresponds to a tetrahedral electron domain geometry. Since all 4 of those domains are atoms, there are no lone pairs on the carbon, the molecular geometry is also called tetrahedral. 4 domains, a tetrahedral electron domain geometry corresponds to a bond angle of 109.5. Since there are no lone pairs or double bonds on the carbon, the bond angle will be exactly 109.5. Next, we can treat oxygen as the central atom. It has 2 single bonds and 2 lone pairs for a total of 4 domains. Again, 4 domains corresponds to a tetrahedral electron domain geometry. This time, however, the molecular geometry is different. Because 2 out of our 4 domains are lone pairs, our molecular geometry is bent. That means that even though our Lewis structure makes it look like the carbon and the hydrogen are directly across from each other in a straight line, in actuality, they make a V shape in 3-dimensional space. Our bond angle is based on the electron domain geometry, which is tetrahedral, so it is approximately 109.5 degrees. Since there are lone pairs on the oxygen, our bond angle is less than 109.5 degrees.